Imagine a plant watering system that knows exactly when your plants need water, can connect to your smart home setup, and give you real-time updates on your plant's environment. Today, I'll be showing you how to create this automated plant watering system using an ESP32-C6. So obviously on the screen now, you can see my circuit, but let me first of all show you the problem. So as you can see on the screen now, plants are dead. What I would like to do is create a system which allows me to automatically water the plants and also monitor other parameters. So what I will be doing for this circuit is including a temperature sensor, a pressure sensor, a soil moisture sensor, and a way to drive a water pump. Now the issue I have with my plants is basically I always forget to water them. And when I do water them, I always end up over-watering them. So this project obviously aims to solve that by sensing the soil moisture level and watering the plants automatically. I will also send all the data, basically the pressure, temperature, the soil moisture levels, all of that to a kind of a smart app if I can get it working, which obviously will take a little bit of time. But so what I will be using for this project is the ESP32-C6 Mini-1 that you see on the screen now, the one with the antenna included on the board. I've heard good things about this in that it's easy to get up and running, so this is what I'm going to do. You can see what you need to get this schematic and this board up and running. So first of all, if I show you what I mean. So let me show you figure 5 quickly first. So if you go to figure 5 and figure 7, you can see the internal schematics of the ESP32-C6 module. And figure 7 has the peripherals requirements that you might need to include. Obviously, if your project's different, then that will change depending on what you need. So internally to the ESP32-C6, you have basically this, where you have your microcontroller, you have a crystal, in this case is 40 megahertz. You have a matching network over here going to the RF antenna, which I spoke about before. You have a power supply, which is filtered using this pi filter. You have another power supply. Obviously, there's some filtering on it as well. So all of these capacitors, inductors, the antenna, that's all included inside the C6 module. And then you have basically all of these pins going out to the module where you can use them to do things that you need to do. So some of the important pins, I think, are chip enable, obviously your power supply, so your 3v3 and your ground. And the other bits, I think the best thing to do is to look at figure 7, which gives you sort of a starting point. So on figure 7, which is basically on section 8, it gives you a brief schematic for the peripherals that you can connect up. And obviously this is the typical application circuit for the module. So the component requirements for this circuit are quite simple in that you have a enable switch over here. You have some JTAG programming headers, but I think you can do the programming through USB as well. So in my case, I will be using the USB. Not entirely sure what IO9 does because I've seen it being used in here and also on the dev kit, which I'll show you next. So I might just include that just in case. Going back to my schematic, I'm just going to walk you through each section step by step. So if you want to build it up, then you can do, or if you want to modify the circuit in your way. The project files will be on GitHub and my Discord. So if you want to join that, then obviously you can have access to the files. But first of all, you have a USB-C connector over here and the 2 resistors that you need for it. So the 2 CC resistors, in order for the USB-C connector to be detected by the host. You have your USB DN and USB DP. So it's very important to label this as DN and DP. I think you can do D plus and D minus as well, but KiCAD needs some sort of reference to designate them as differential pairs when it comes to doing a differential pair layout on the PCB design. Next, I have a TP405 LiPo battery charging circuit. I've been through this circuit in the past for one of my power supply videos, so if you want to understand how it works, you can check out that video. So this battery voltage will go to a 3v3 buck boost converter. So I've used this part in the past and it works quite well. You have some input capacitors to stabilize the voltage coming in. So you should have about 4.2 volts to maybe 3.6, 3.2 volts coming in over here. So that's basically the battery voltage range. That voltage goes to the regulator, obviously, and we have a output voltage of 3v3 over here. Now I do have a 5-volt boost converter as well. This is needed for the motor, and the boost converter is a TPS61240. So obviously you can see from the pin out, it's a very simple part. Just 2 capacitors and an inductor to get this thing running. And it's a 5-volt fixed output, so the feedback is connected directly to Vout. So I don't need a feedback network for this part as well. One of the things you might have noticed with these 2 regulators is that the enable pin basically goes to the microcontroller. So I'm using GPIO 0 and GPIO 1 to turn on and off the 3v3 and the 5 volts. So 5 volts I can turn on when I basically want to run the motors, and then I can turn it off. Whereas 3v3 is a little bit more special because the 3v3 also powers the chip. So powers this ESP32-C6. Now the way I'm doing that is with this circuit over here, which I've called the power on control circuit. So as you can see on this circuit now, you have a V battery voltage coming in from over here. You have a small resistor going to a push switch, and there is a secondary switch over here, which is a slide switch. And I'll talk more about that a little bit later. Then you have a pull down resistor, 150K, and you have this pin over here, or this label, which goes to the microcontroller as well. So that's detection on and off. And you have a 220 ohm resistor and a 100 nanofarad capacitor, as well as a diode. The output from this circuit, which is basically enable 3v3, goes to this regulator over here. So it goes to this pin. Now, when the user presses switch 2, which is a push button, what will happen is that the voltage over here will go up, which will enable this regulator. And when this regulator is enabled, basically the power to ESP32-C6 will go on. And as soon as this is powered on, what I want to do is set this output as high. So what I'm going to do is set this as high from this side. So then the user can release the button and the microcontroller will basically stay on, as the microcontroller is holding the 3v3 enable high for this regulator. Now, if the user comes back and wants to turn the circuit off, what they can do is press this button again. So pressing this button will send this point over here. So you can see it's pulled down by a 150K resistor. Pressing this button will connect the battery voltage to this resistor over here. So what you will have on this side over here is basically a potential divider 1K, 150K, which gives you, when the battery is fully charged, a voltage of approximately 4.2 volts over here, slightly less than that. And obviously when the battery is discharged, then it'll be close to 3.2 volts or whatever it is. Now, one of the limitations with this circuit is that obviously you can't program it because there will be no power to the board. So this is why I've included this slide switch as well. So this slide switch is just for development and nothing else. One of the things I want to make sure is that the enable pin can handle the 4.2 volts. So obviously you're going to have 4.2 volts over here. Then the current going basically this side is going to be very little. The input resistance of this pin is going to be very high. So the current going into it is going to be very high. There will be a little bit of voltage drop here and a little bit of voltage drop here. So on SS14, you can look at the forward diode voltage drop, which is basically going to be less than 0.2 volts, basically, because we're using SS14. We're going to have very little going through it. So the voltage will drop to 4 after the diode, and we do have the resistor in place, which will drop a tiny amount of voltage as well. Now, just thinking about that calculation again, I think it might be a good idea to increase the value of this resistor over here so that you don't get to, you know, above 3.3 volts on the input pin. So I might change that to like 15K, which would give us roughly 3.5 volts maximum on this. And then that would fall within the specification of the microcontroller. So if you're just looking at this, the microcontroller can handle VDD, which in our case is 3.3 volts plus 0.3, so that's 3.6. And we're going to have a little bit of drop on our diodes. So we should be okay with a 15K and a 150K over here. Another thing I can do, maybe just decrease this. So if I go to 75K on this side, I'm going to change that to 10K. And I'm going to add a parallel 150K resistor over here, just because I don't want to increase the BOM lines too much. I don't have anything else that's close to 100K. So 2 of them in parallel will give me 75K, which will make sure that this voltage doesn't get too high. So the only calculation I'm doing there is basically the potential divider equation. So I've got 10K on top and 75K on the bottom, which gives me a output voltage of over here 3.7 volts when my battery voltage is 4.2, and when the battery voltage is 3.6 or 3.2, then this voltage is going to be 2.8. The threshold for the enable pin is 0.8 volts. So what I'm going to do is basically add another resistor over here, so 20k on the top resistor, and I've got 75k on the bottom resistor over here, which will give me precisely 3.3 volts when the battery voltage is 4.2 and 2.5 volts when the battery voltage is falling to like 3.2 volts. You can see over here, this is just basically two header pins or header sockets for the battery connection. The main thing in this obviously is the ESP32-C6. This will handle all the data from the sensor, make all the decisions to control the motor, what to set on the display that I'm going to show you next. The soil moisture sensors are analog, so they are going to the analog pins over here. So the analog voltage from the soil moisture sensor will be converted with the ADC channels on the ESP32, and then we can do what we like with it. So we can set our thresholds and things like that. I'm using USB on this, like I said before, and I'm also basically doing a I2C, and this is a shared channel for the display and the pressure sensor. The pressure sensor comes with a temperature sensor as well, so I should be able to get temperature and pressure from the same device. Obviously, the ESP32 will help us connect to the home network so that we can do notifications and, look at the temperature data, the soil moisture data, and all of that remotely. I think that's going to be a long-term project because I've never done anything like that, but it'll be good fun to learn. So I've kind of briefly mentioned some of the other things on this. So I have a pressure sensor, which I'm using a BMP388, which is a barometric range, I think. So should be sufficient for what we need in this case. And I don't really need to read it too fast as well, so I2C will be fine as well. It does have an interrupt and a chip select, but I won't be doing that because obviously I'm on I2C. So I've just connected it up just in case I need to. The I2C, I'm using 5K 1 pull-ups, and that's just because I'm using those resistors over here as well. Again, I don't want to increase my bottom lines if I don't have to. Now, this is a header pin for a display module that I've ordered from Amazon. I'll leave a link in the description below if you want to get one as well. For the display, I've basically ordered this OLED display that works on I2C. So you got SCL, SDA, 5 volts. I think this runs on 3v3 as well, and a ground input. So simple 4 input interface, and a very small display where we'll be able to display out all the information that we need to. Obviously, there's not a lot to display here, so that should be okay. Just going through the display, it's relatively high contrast, and the viewing angles are pretty good on OLED displays as well. So it should be fairly easy to use. I don't have a driver for it yet, but I'm sure there'll be some available online, so we'll be able to use that. Obviously, the active area is quite small for this display, but I think that's a good thing because we'll have a relatively small PCB, and obviously I don't want to drive too much current into this because we are running on a battery as well. That kind of reminds me, we might want to set this up so that we can turn the display on and off. I know there are some internal features on the driver of the display that lets you turn the LEDs off. So maybe that should be enough in terms of power saving. I'll see how long the battery lasts, and if it doesn't last that long, then we will have a look at alternatives. We've got the 2 analog moisture sensors. Again, they're connected through a header. They need 5-volt power supply, and they provide an analog output, which is going to our microcontroller. And this is the motor, the water pump, motor driver, and the soil moisture sensor that I'm using for this. They give you a handy interface diagram for an Arduino. Obviously, we don't need that. That'll be fine. We have 5 volts ground going to this, 5 volts ground going to this. Obviously, that goes to the motor. And we have a motor drive controller basically, so we just need to turn it on and off. I have a relay board which will control the motors. The motor control board will basically drive the motor, so I don't have to worry about that for this project. And I've got two moisture sensors and 2 pump controls, just in case I wanted to have 2 plants. So let me quickly show you the sensors and the motor driver that I'm using for this project. So what I've done is basically ordered this capacitive soil moisture sensor, feeds some frequency into the kind of the capacitor coil that's kind of into the PCB over here. So I know there is a timer in this circuit over here, which obviously I think runs at very high frequency. And basically this capacitor is charged through a resistor somehow. And the time constant between them is used to detect the soil moisture levels. So if the soil moisture is high, then I think the capacitance is higher as well. But I am going to test that. I'm going to test this circuit to see how it works. Maybe we can build our own in the future as well. I have a motor driver here and a motor with a water pump and a tube as well. So this obviously product makes it very easy to build this project. And if you want to follow along, I've got some links in the description below. Now the motor driver is just a relay, and we have an on-off control, which is obviously coming from our ESP32 PCB. And we have 5 volts that's coming in here as well. So this is the circuit for our automated plant watering system. Obviously, it's not too many components, as you can see. I've managed to fit the schematic onto one page, so that's always a good thing. It's going to be relatively simple, but I think a good tool for me to learn about ESP32 and share my learnings with you guys as well. So let me know what you think. If you think I should include something else, or if you think I've missed something from the ESP32 board, because I am currently going through the PCB design for this, so I can make changes. Thank you for watching today. Don't forget to like and subscribe for more electronics projects. See you next time.